In this video, we're going to look at some conceptual examples that involve dimension. Okay, so here is the first example. So let's let W be a subspace of some vector space V with the dimension of W being equal to 6 and the dimension of V being equal to 8. And I have a true or false question. And I need to justify my answer with an explanation or a counterexample. Okay, so part A of this problem is the following. If the set of vectors v1 up until v6 is a basis for W, we can selectively add two vectors to the set to get a basis for v. Okay, so let's think about this. So we have these 6 vectors. They're a basis for W. And it makes sense that a basis for W would have 6 vectors because the problem tells us that the dimension is 6. So it's saying that we can selectively add 2 vectors to the set to get a basis for V. At this point, I'd encourage you guys to pause the video for about 1 minute and think about this. And my hint is maybe review your notes from the earlier videos of this section and think about, is there a theorem that tells us something to this effect? Okay, so 4, 3, 2, 1, pause the video. Pause the video for about a minute, review your notes, and see, is there a theorem that tells us something like this? Okay, so hopefully you guys did that. Hopefully you guys paused the video for about a minute and thought about it. So let's start talking about this. It turns out that this is true. That if I have a basis for my subspace, I can add vectors to it in a selective way to get a basis for the larger vector space. So here is the theorem that I was sort of alluding to. The theorem is, if we have a linearly independent set of vectors in whatever vector space we're talking about. Okay, so if we have a linearly independent set in V, this can always be extended to a basis for V. So the picture for this is, like if I have this circle representing my vector space V, and then W is some subspace within that. So we have a basis for W. We have a basis for W, and that basis has 6 vectors in it. These 6 vectors. Conceptually, if I add a vector to the set of 6 vectors, that's not in W. So let's say I have some other vector that sort of like lies outside of W. If I include that in my set, that now enlarges this subspace. It enlarges the possible span of the vectors. So that'll happen when I add one vector to my set, and then when I add a second vector to the set, now I have 8 vectors. And if I have 8 vectors, it's got to be all of V. So using the idea of this theorem, what we would do is we would add 2 vectors to get 8. I'm going to call them 2 good vectors. We would add 2 good vectors to get 8 linearly independent vectors. So that's what I mean by good. That when I add them to this list of 6, that the 8 vectors now are going to be linearly independent. And if I have 8 linearly independent vectors, well, that is guaranteed to be a basis for V. Because the dimension of V is 8. So if I have 8 linearly independent vectors, that is guaranteed to be a basis. So let's do another example. Okay, so part B of this problem is, well, now let's say we have a set of 8 vectors, V1 up to V8. That is a basis for V, for the vector space. Then some set of 6 of these will be a basis for W. Okay, so this is another good conceptual problem. With this one, I want you guys to pause the video for about 2 minutes and think about this. So 4, 3, 2, 1, pause the video. Pause the video for about 2 minutes and think about this. So let me give you guys one hint as you are thinking about this. So my hint is, when we have vector spaces or subspaces with high dimensions, like higher dimensions, relatively speaking, like 8 and 6. Often it's, we can make the problem a little bit simpler if we think about an example in smaller dimensions. So let's say that V was something like R2, and we had a basis for it. So let's just say that the basis is E1 and E2, the standard basis. So remember, E1 is the vector 1, 0, E2 is the vector 0, 1. And now let's say W is some subspace in R2, but that has a smaller dimension than V. So let's just say W is, for example, a line through the origin. Let's say it's the line y equals x. So W is this line, y equals x, for example. Okay. So think about the two vectors that we have, E1 and E2. So here's E1. And here's E2. In the context of this example that I'm looking at, what I would be asking myself is, can I remove either E1 or E2 from this list so that I have one vector, so that that one vector spans W, that one vector will be a basis for W, this blue line. Okay, so at this point, pause the video for another minute or so and continue to think about this. And if you feel like if you have an answer to this parallel problem, then try our original question. Okay, so 4, 3, 2, 1. Pause the video one more time and think about this again. Okay, so hopefully you guys have done that. Hopefully you guys have paused the video, and it's been a minute or so for you guys, just a couple of seconds for me. Let's talk about this. So I wanted to do this parallel problem here on the side to help us get an intuition for whether this is true or not. Okay, so at this point, by looking at this parallel problem, I see that, if we were to remove either E1 or E2, then we definitely won't have a basis for the line y equals x. Because if we remove either E1 or E2, our span would be either the x-axis if we removed E2, or if we removed E1, the span would be the y-axis. But in either case, it wouldn't be the diagonal line. So that's going to give me an intuition. Okay, so this is going to be false. When I remove vectors from the basis of the larger vector space, there's no guarantee that I'm going to get a basis for the subspace. Okay, so here is an example. Let's do a counterexample. So what I'm going to do is, I'm going to think of W first. I'm going to think of the sort of the analog of this line y equals x. And the way I'm going to do this, so I'm going to let W be represented by the span of the columns in a matrix. Okay, so my idea is to have something like we had in this picture. I'd like the vectors in V, the basis vectors, so those are the E1 and the E2, to lie completely outside of what W is. Like W was this blue line for me. So one way I can see that quickly is if I guarantee that the things in W have some entry that's always 0. So if I make a matrix, and W has to have dimension 6, so I need 6 pivots. So let's just say the first column is E1, the next column is E2, so 0, 1, 0, dot, 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 dot. And then I keep going like this, so that the last column would be 0, 0, 0, 0, 0. I'd have a 1, but then 2 zeros underneath that. Okay, because I only want 6 pivots. So this matrix has 6 columns. 6 columns. But underneath this 1 in the last column, we have some zeros. Whoops, sorry, I think I wrote a 1 here when I meant to put a 0. Okay, so what I'm going to do now is I'm going to construct my vectors v1, v2, up until v8. Okay, and it helps me to visualize this if I just think of them as columns in a matrix. So what I need to do is I need to make sure that v1 up to v8 forms a basis. So I need to make sure that there's going to be a pivot in every single row and every single column when I row reduce my matrix. In other words, I want my matrix to be invertible, but I want the entries in these bottom rows to be non-zero so that they don't match up. The easiest way for me to do that is if I let v8 be like 1 and then 0 is all above it. And then the vector right before that would be 1, 1, and then 0 is all above it. And then we keep going like this until we get to the first vector, which will just be 1s all the way up. So the second vector would have been a 0 at the top, and then 1s completely underneath that. And then we'd keep going like this. Okay, so the diagonal entries are all non-zero here. So one really quick way to see that this matrix, the columns are linearly independent, and that they span my vector space, so in other words, that there's a pivot in every row and column, is to check to see if it's invertible by looking at its determinant. So the determinant of this matrix, because it's triangular, is just going to be the product of the diagonal entries. So it's going to be 1 times 1 times 1 times 1, which is 1. And that's not 0, so that means this matrix is invertible. Okay, so because it is, that means these vectors v1 up until v8, they are a basis, in my example, for R8. And why this is good for us is we can't remove two of the vectors, two of these vi's, and get a basis for w because none of these vectors, none of these vi's are even in w. Because when I take the span of the columns in this matrix, the last two rows should always have 0. But none of the vectors, none of the vi's have that property. The bottom two entries in all of these vectors are always non-zero. So as a result, if I try to remove two of them, it's definitely not going to be a basis for w, because when I remove two of them, I'll end up with vectors that are all not in w.